Okay, so we rationalized yesterday. Yes, okay. So addition and subtraction. Of radical expressions. So like I was saying earlier, those symbols, so the radical symbols, they're just symbols that represent numbers. And so we're going to treat them just like we treat variables. So if I have like 4x plus 3x, that is equal to what? It's not a trick question, I promise. 7x. Well, I don't really want to write it there. I'm going to write it here. Right? So these are like terms. But if I have like 4x plus 3y, that can't be simplified, right? Because they're not like terms. So can't be simplified. Because these guys are unlike terms. So the same thing is going to work if instead of an x, we have a radical symbol. So if I have 4 times the square root of 3 plus 3 times the square root of 3, what do you think that's going to be?
Oh, nice.
7 times the square root of 3 or 9?
3. Good. So imagine taking the expression over here and just replacing the x with the square root of 3, right? Just like the x doesn't change when we add 4x plus 3x, the square root of 3 isn't going to change when we add 4 times the square root of 3 plus 3 times the square root of 3, right? So at this point, we're just counting up how many square roots of 3 we have. Just like over here, we're basically counting x's. So it's like, what happened?
I don't know.
There could be something dead under the heater. I wouldn't put it past us. So just like here we're like counting up x's, here we're counting up square roots of 3. And so the square root of 3, once we've simplified a radical, we can't change what is under the radical symbol. Like we can count them up, but we can't change it unless we're multiplying or dividing. So if I have 4 times the square root of 3 plus 3 times the square root of 2, that cannot be simplified. For the same reason that this one can't be simplified over here. They're not like terms because the factor after the coefficient is different. So it would be like if I put on my shopping list 4 apples and 3 oranges, like I'm not buying 7 of anything, right? I mean, 7 pieces of fruit, but not 7 apples or 7 oranges. So these are not like terms, and so they can't be combined, whereas these are like terms, so they can be combined. Just because this is one that trips people up every time. What is x plus x equal to? How many x's?
To the second.
2x.
2x. Right, because that is 1x plus 1x. In general, when you add and subtract, it changes the coefficient, so the number in front. And when you multiply or divide, it changes the exponent. So here we're adding, and so we have 1, 2 x's.
So why wouldn't up at the top that be
8x.
2 square root of 3?
Because this is saying I have 1x and I'm adding another 1x. So I have 2 of them. That's saying I have 4 root 3's and I'm adding 3 more root 3's. And so I have 7 of them.
Oh, okay.
Is that imaginary?
I'm with you.
1/5.
It's not imaginary. It's the reason that it's not written is because 1 times x is equal to x, right? So it's not that it's like imaginary, it's that we simplified 1 times x to be x. So then what would the square root of 3 plus the square root of 3 be?
3. Well, no, it would be, would it be 0, 3, or, I don't know.
So let's remember that the square root of 3, that symbol is going to behave just like an x.
So 2 square root of 3?
Yes, very good. Because I have 1, 2 of the same thing. So when you're adding and subtracting, it really is like, I think of it like a shopping list, right? Like if my kid put like banana on the shopping list and then my other kid put banana lower down because they didn't realize that it was already written, I would buy 2 bananas, right? I mean, there's no such thing as a banana squared, but like, I definitely wouldn't. But that's like what we're doing here is we're just like, but if one of my kids put 4 bananas on the shopping list and my other kid put 3 bananas lower down, I'd buy 7 of them, right?
Sure, I could do it.
Well, I would buy as many bananas as they want because bananas are very healthy. And that's not the type of thing my kids put on the shopping list.
Only if you're active.
They were like,
Yeah.
that's
right.
true.
Too much
They
potassium
have
is
a
not
ton
good
of
for you.
sugar in them.
Yeah.
And a
So-
lot.
But they have
Yeah, there's
potassium
something engineered.
which regenerates muscle growth.
They're not even real bananas anymore.
What are you talking about?
They're not the original bananas. There's no seeds in them anymore. They're genetically modified bananas.
Oh, I'm
must
sure
have been the ones
everything's
they got from
genetically
the moon,
modified.
Right, see? Neil Armstrong brought them back.
So these two things, those are the same thing, right? We have 4 of something, we're adding 3 of the same thing, so we end up with 7 of them. Here we have 1 of something, we add 1 more of the same thing, so we end up with 2 of them. So it's the same exact idea when we're adding and subtracting. So the key here is that we need to simplify before we combine like terms. So this is the one thing that makes it slightly different than when we're working with variables, is that sometimes you can simplify the radicals before you add and subtract. So for example, that was the best game.
I think of those banana for scale beans.
Square root of 90. So here we don't have any like terms, right? So there are no like terms.
It would be 6, 0, but 8.
So we can't add or subtract those. However, when I look at the square root of 40, the square root of 50, and the square root of 90 individually, I notice that I can factor 40, 50, and 90, just like we did yesterday, to potentially simplify those radicals. So here I have 2 times, this is 2 squared times 2 times 5. And then this is, let's see, 5 squared times 2. And then this one is 3 squared times 2 times 5. So then I have 2, and then remember the operation between the coefficient and the radical is multiplication. The square root of 2 squared is 2. And then the square root of 2 times 5 is just the square root of 2 times 5 because neither of those can be simplified. And then I have 4, and the square root of 5 squared is 5. And the square root of 2 is the square root of 2. And then the square root of 3 squared is 3. And then the square root of 2 times 5 is just the square root of 2 times 5 because neither can be simplified. So we end up with 4 times the square root of 10 plus 20 times the square root of 2 minus 3 times the square root of 10. And once we've completely simplified each term individually, so simplify each term, so just on its own as if it's its own little expression. Now we can see if there's like terms to combine. Do I have any like terms?
The square root of 10.
Right, so I have 4 root 10 minus 3 root 10, which leaves me with just 1 root 10. And then plus 20 root 2.
Yeah, can we have a negative in that position?
You can have a negative coefficient. You can't have a negative radicand.
Right.
Yep. So remember, the coefficients are just counting things. So if I have 4 of something and I take away 3 of the same thing, that's okay. So let's try. Let's do this. We'll simplify. Okay, so same idea here. We see that we have no like terms to combine, and so we're going to look at each term individually, and we'll start with prime factorization. So this is 5 times the square root of 3 squared times 2 minus 3 times the square root of 3 squared times 3 plus 2 times the square root of 3 to the 4th plus 5 times the square root of 3 squared times 5.
Can you do the least common multiple?
Of what?
I don't know, figure out what all the, you have, kind of like you do when you multiply, you know, if you have 18, 27, 80, you want to find all the least common versus the most common.
Do you mean the GCF?
GCF, yeah.
Well, yeah, we can do that. We'll do that in a sec.
Oh,
I mean, just to show you. Like,
it will come out the same, though, right?
well, so it's a different process.
Different process, but you get the same answer in the end.
Well, I mean, like, it would be a different question.
Oh, it is.
Yes. So I'll show it to you when we're done simplifying. I'll show you what it would look like to factor it. So we have 5 times what?
3.
3,
Mm-hmm.
and then 2.
Mm-hmm. Good.
Squiggly.
Minus 3 times
3 root 3.
3 root 3. Good. Plus 2 times
This
3
squared.
Very good. Plus 5 times.
3, 5.
Very good. So I have 15 times the square root of 2 minus 9 times the square root of 3 plus 18 plus 15 root 5. Can that be simplified any further? Correct. I can't simplify that any further because I don't have any like terms, right? Notice when we look for like terms, we're not just looking at all the numbers, we're looking specifically at the radical factors. And because none of those are alike, we cannot combine them. Can I add these two?
No, because it would be a different.
Correct. That would be like trying to add 18 plus 15x, right? So because that root 5 is being multiplied by the 15, I can't add the 15 and the 18 because that multiplication takes precedence. So, Mike, what you were asking is if I could like factor it.
Yeah.
So this is fully simplified. Remember that factoring isn't simplifying. But if I wanted to factor this, I could say, okay, they all have a common factor of 3, and I could call this 3 times 3 root 2 minus 3 root 3 plus 6 plus 5 times the square root of 5. And we will have occasions where that's convenient, like if we have a fraction and we want to simplify the fraction, we can factor out common factors so that we can cancel common factors in the numerator and denominator.
Could we
What's
do
up?
that at the very beginning?
Well, so what?
Like if we all
So-
see that they have 9.
Well, but
Yeah,
they
see-
don't all have 9. They all have the square root of 9 in common.
Is that first one correct, though?
What do you
3
mean,
squared
correct?
2?
Oh, I'm
Because-
sorry, that's a 5.
Okay, thank you, because I'm like, wait a minute, that don't equal
So-
15. There we go.
When you say could we, that's like what I want to emphasize is that what I just did isn't the next step of the problem I gave you.
Okay.
Like this is the answer to the problem I gave you
You
because
still
it's
have to do one
simplified.
more step after.
No. This is the answer to the problem I gave you.
Right.
Factoring and simplifying aren't the same thing. This is a different problem.
Oh, so it's not the same answer as the simplified when you multiply?
No, because factoring and simplifying are different things. This is simplified. This is factored.
Gotcha. They're the same.
If I gave you, they are equivalent expressions, they are different processes. So if I gave you 2 times 3 and you wrote it as 6, that would be simplifying. If I gave you 6 and you wrote it as 2 times 3, that would be factoring. We factor for a specific purpose, like to simplify fractions, so we can cancel common factors, or to solve equations. Like we have lots of reasons to factor, but it's not an additional step to the simplifying process. This, everything above this line is simplifying that expression. This is factoring it, which is a different thing. So, like I told you guys last week, like when we do these things in practice, they will be a part of bigger problems. And so it will be obvious what form we want it in order to do what we're trying to do in the bigger problem. So for instance, if, I mean,
just weird how that comes out. If you multiply it, the factor comes out to the same as the, I know it's different, I'm just saying it's weird how it
No, it's
comes out simplified.
I'm not saying I'm not saying it has a different value. I'm saying it's a different problem.
Right.
So you can have like
understand
two
that.
different. So I mean, it should come out to the same
Oh, it
thing
should?
because,
Okay.
well, that's what it means to factor, right? Is
Right.
to write something as a product. It doesn't mean to change its value.
Oh.
Like when we write 6 as 2 times 3, it still has the same value. Otherwise, there'd be no point in factoring, right? If it completely changed its value, then we have a completely new
Well, I
problem.
guess I just didn't get that could result in, it was connected. I don't know, but I see what you're saying.
So if I have like this problem, or I didn't want to say simplified, I wanted to say simplify. Like if I gave you this problem, then when you simplify the numerator of that fraction, you would get this. So you go like this. But if you want to simplify the fraction, then you would have to put the numerator in factored form, right? Because factoring the numerator and denominator is the only way that we can simplify a fraction. So we would write this as 3√3 plus 6 plus 5√5 over 3 times 2, and then we can go like that, which simplifies the fraction, right? So this is the fully simplified version of the numerator. However, to simplify the fraction as a whole, it is convenient to factor the numerator so that we can then cancel common
You can't touch
factors.
anything within the parentheses.
Correct.
Because it's
Because they're being added
Right.
and subtracted. So the process of simplifying versus factoring it's apparent which one you want to do based on the problem that you're doing. So a lot of the things that we're learning to do are just skills or tools that we will use within larger problems later, but we have to practice them on their own just to develop the skill. Okay,
thanks.
of course. So let's talk, well, here, you guys try this one. Let's do one before we start multiplying. Simplify square root of 45 minus 2 times the square root of 20 plus square root of 12 minus, I don't know. Yes, let's do that. So go ahead and simplify that expression. Is that what you guys got?
Yes.
Well, ahead and look it over real quick if you got something different, just to find where it went wrong.
I had something different on the second line at the very end. I put 5 cubed for some reason.
So 125 is 5 cubed. I just wrote it as 5 squared times 5, because then I can take the square root of 5 squared and take the square root of 5, right? So it's just like when we write like the square root of like x to the 5th as the square root of x to the 4th times x, just to break off that even exponent. So you can do that in your head if you're comfortable with it, or in a second step. Either one is fine.
So you do the 3 minus 4, so you get -1.
Yes.
And then you subtract that by the 5.
Uh-huh.
But wouldn't that be a -5? Or is it?
Yeah, so we're subtracting positive 5, or we're adding -5.
So it'd be -9.
Because I just got 4, because I did
Oh, never
-1
mind. I
minus
forgot
-5, so then I switched it to a
So
plus.
it's 3 minus 4 minus 5. So it's not minus -5.
So it's a +5, we're just subtracting.
Yes, or we're adding a -5. So that negative sign can either be subtraction or it can be a negative sign. It can't be both. So we can't subtract a negative. We can either subtract a positive or add a negative.
Okay, got it.
But we can only use it once.
Okay, so I could like switch it to addition if it was like in parentheses and like a negative.
Right, you could go like this.
Okay.
Very
But
good.
essentially, that's what it is. 'Cause
Yeah.
it's under the,
Right, they're equivalent.
right.
It's just like it's tricky sometimes because we look at the minus sign and we think, oh, that's a negative number, but then we also want to do subtraction. So you just want to remember that it's either or. Other questions? Okay, so let's move on to multiplication. So yesterday we multiplied radical expressions. Today we're going to multiply expressions that contain radicals and addition, subtraction. So really, when it comes down to it, the way all of these behave is just like polynomials. Just like what we did here, when we add, we're adding like terms. So the same thing is going to be true when we multiply. So let's do... We'll start with just like the square root of 3 times 2 root 3 minus the square root of 5. So notice that in the parentheses I have 1, 2 terms. And so just like we do with polynomials, we're going to distribute that square root of 3 to both of the terms in the parentheses, right? So we're going to multiply the square root of 3 times 2 root 3, and we're going to multiply the square root of 3 times the square root of 5. So we have the square root of 3 times 2 times the square root of 3 minus the square root of 3 times the square root of 5. And then within each term, you can multiply radicals and you can multiply coefficients. So in that first term, I can multiply the square root of 3 times the square root of 3 to get the square root of 9. So this is going to be 2 times the square root of 9. And in that second term, I can multiply the square root of 3 times the square root of 5 to get the square root of 15. So now this is just like one of the problems we were just doing, where I can simplify each term individually. So the square root of 9 is 3, so this is 2 times 3. And then the square root of 15 doesn't simplify, right, because it just factors into 3 times 5. and there's no perfect squares there. So that's just going to stay the same. So we get 6 minus the square root of 15. So just like when we're multiplying polynomials, we want to distribute to each term. So terms, again, are separated by addition, subtraction. So we're multiplying the factor on the outside by each term individually. What's up?
Oh, no, so the only reason you put the multiplication symbol in between is just to separate the two out?
Yeah.
Because, I mean, you don't need it over on the 3 square root of 3 square root of 5, right? Because it's automatically multiplication without the symbol.
Well, it's multiplication either way.
I'm just trying to understand.
It's not about a need or a don't need. It's just I have to write multiplication one way or another. And so sometimes I write it one way and sometimes I write it another. Like it's, I didn't put it there because it needs to be there.
No,
I just put it.
about up to the 3, 5, in between the 3 and 5.
Do you mean the square root of 3 and the square root of 5?
Yes.
Okay.
You don't have to put a multiplication symbol.
Right, like I said, it's not about if I need it or don't need it. It's about I have to write it one way or another, so I pick one.
Well, that's what I'm trying to figure out is which way to write it.
But there's no right way to write it. You just pick one. That's what I'm trying to say. Is it's not like I wrote it there because
I can put some over there and not put some over there, and it's okay.
I am not saying that in every situation you can do whatever you want. I'm saying in the case of multiplication, there are multiple ways to express it.
Yes.
And which way you express it is up to you. Sometimes to me, sometimes it seems more convenient to express it one way or another. Like I use dots sometimes to separate things that people often think go together if I don't separate them. Like when I write 2x in a fraction, and it's hard for people to see that you can cancel the 2 independently of the x, then I will often put a dot between the 2 and the x so that people can see that they're separate factors.
So if I want to be a rebel, I could put 2 in parentheses.
You can do whatever makes sense to you.
Okay. I'm just trying to see if there's a right or a wrong way to do that.
No, so with multiplication, the different ways of writing, it's just like what we just talked about with the subtraction, is you can write it as addition of a negative, or you can write it as subtraction of a positive. They're equivalent. You just pick one that makes more sense to you. Multiply two binomials. So we will multiply, let's do the square root of 3 minus, or no, plus 4 times the square root of 5 times 3 minus the square root of 5. So just like with polynomials, we have 2 terms in that factor, and we have 2 terms in this factor. So we're going to distribute the square root of 3 to both factors, or both terms in the second factor. So I have the square root of 3 times 3 minus the square root of 3 times the square root of 5. And then we're going to distribute 4 root 5 to both terms in the second factor. So here and here. So we've got plus 4 times root 5 times 3 minus 4 times root 5 times root 5. And now we're going to simplify in each term, right? So keep in mind that terms are separated by addition and subtraction. So we've got 4 terms. So we're going to do whatever multiplication we can do. So we've got 3 times the square root of 3. 3 is not under the radical, and the other 3 is under the radical. So all I can do is put them together. And then here I have the square root of 15 In that third term, 4 and 3 are coefficients. So we'll multiply the coefficients, and then we're left with the square root of 5. So again, you can multiply radicals, and you can multiply coefficients. But you can't multiply a coefficient by a number that's under the radical. So then we have a coefficient of 4, and root 5 times root 5 is root 25. Now we're back in the situation we were in when we first started today, where we're adding and subtracting a bunch of terms. So we want to simplify each term individually. 3 root 3 cannot be simplified. The square root of 15 cannot be simplified. 12 root 5, whoops, I wrote a 5 when I said a 3, I'm sorry. This is a 3. 12 root 5 cannot be simplified, but the square root of 25 is 5. So we end up with 3 times the square root of 3 minus the square root of 15 plus 12 times the square root of 5 minus 20. And that's as far as we can go because I don't have any like terms. So even though it's somewhat ugly, I can't go any further than that. To simplify. So this step right here, you will probably be able to skip eventually. But if you find yourself making mistakes, if you're trying to do the multiplication in your head, then you should write all the factors out so you can see them all as you're doing it. So here's one for you guys to try. Let's do the square root of 3 minus the square root of 6 squared. Can't think of what could possibly be sneaky about this.
We'll see. Unless I'm just totally stupid, which is probably correct.
I don't believe that those are the only two options.
The only two I can think of right now. Oh, that's right.
I think you should start your own like conspiracy theorist YouTube channel.
Well, because yeah, the first one was correct. I'm stupid, so
No.
because I combined 6 and 3.
Well, making mathematical errors does not make one stupid. It makes one in the process of learning. If you don't make any mistakes, you never learn anything.
What I think is sad, the thing I'm going to remember most from like this specific class is there's no square root of a banana.
Yeah. And at the
I didn't even say that. I said there's no banana squared.
Yeah, see, you got it wrong. And then remember, the moon landing was faked. Well, I still got the same thing.
So 3 minus, this is 3 squared times 2. So we end up with 9 minus 6 root 2.
Wow.
So how the hell did I come up with your third line and not your second?
I don't know. You tell me, because I can't see what you did.
Multiply it. Oh, so you just wrote it all out instead of doing it in your head.
Well, did you get the same answer?
Yeah.
Oh, good. Ben, talk to me. How far down are we?
So the third line is where I started to do
Right here?
Yes,
Above or below that line?
below it.
Okay. So what did you write here?
I wrote 9.
Did you write the square root of 9?
Mm-hmm.
Okay, that's fine. That's the same as the square root of 3 squared.
And then I did have the 18 minus 18.
Root 18 minus root 8. Yep, uh-huh. And then this could be the square root of 36.
Yeah,
Is
that's-
equivalent.
That's where I messed up. So I wrote that as a 12.
Oh, okay.
And I see what I did wrong.
Yep, no biggie.
The signs keep messing me up. Like I didn't get 9.
Oh, did you get -3?
Yeah.
So it may be, one thing to keep in mind is that you use the sign to the left of each term, right? So you don't want to go 3 minus 6. You want to go 3 plus 6. So the sign to the left of each term as opposed to using anything to the right of each term. Like this term ends right here. And then this term is like this, and this term is this, and this term is this. So we have 3 and then plus 6. Does that make
Right.
sense?
I thought it was neat. Technically, you have a -36 and a plus 36.
Well, you technically you don't
Well,
have a -36 anywhere.
I did, but I still came out with the same answer.
Well, but then that means that you made 2 mistakes that undid each other. So you should look into why that happened. Because this right here is not like this. Because remember, when you're adding and subtracting,
Oh, okay, so
you can't change what's under the radical. Just like if I had -x minus x, the x doesn't change, it's just -2 root x. We could have written,
So you can't write that square root of 36 then? 'Cause it's
no, which one?
the
This
negative
is
18.
no, it's not the square root of 36. So remember yesterday we did this, this thing? Whoops, sorry, that was a 6. We did both of those and we found that they're not the same.
Yeah, but those two are the same.
Right, but what I'm...
The 18 and 18.
Yeah, I know that. What I'm saying is that when you add 2 things under the
Oh.
radical, it's not the same as adding the 2 separate radicals.
Right. but-
So if you have -root 18 minus root 18, it's not the same as -18 plus 18.
no, I-
Doing it outside isn't the same as doing it inside. So there's
so it
no
can't
way to
be
get
36
36.
either.
Because we can only combine like terms. So these are like terms, which
Right.
means we have 2 of them.
Okay. It's just.
Sorry, that's a negative.
Right.
Which we could have done here. We could have said this is -2 root 18.
Okay.
And then simplified.
I just got lucky then.
Right, that's an alternate way to get to that, is combine like terms first and then simplify. But notice that we never change what's under here. You can never add or subtract radicands. You can only add and subtract coefficients.
So if I would put 2, well, -2, that would have been fine.
Right,
Without the 36.
right.
Gotcha.
So when it comes to adding and subtracting, the numbers that you can add and subtract are only the numbers that are in front of the radical. So that's this. Those 2 are coefficients, right? So they can be added. These 2 are coefficients, so they can be added or subtracted, as the case may be. God, those freaking ROTC people, I tell you what,
Same
they
with those two.
They have like the heaviest footsteps in the
If you
world.
wanna join ROTC with me, like, I had this thought that I could be
Could we actually
the
join
worst cadet
ROTC
ever.
still?
I think we could do it until they ran our social security numbers. Like,
Yeah.
we might get to do it for a day.
That'd be cool.
Just
It'd
for
be
the
a
heck
really-
of it.
It'd be a really
Tell
fun
them
day.
about reality and not their make-believe little.
When I stay at work really late, like when I spend the night here, they come and start running stairs at like 4 a.m. Like literally like running these
Why
stairs.
don't they go to the
I mean, they do all sorts
I
of
hate
stuff
running
out there,
stairs.
but
Oh,
it's crazy because it sounds like a herd of freaking elephants at like 4 in the morning.
70-pound rucksack, that's fun.
Okay, let's simplify.
Anyway. Those are my younger years. It all went downhill.
Yeah, let's do this. 3 plus the square root of 2 times 3 minus the square root of 2. And tell me what you get. Is to rationalize denominators when the denominator has more than one term. So rationalizing denominators with 2 terms. So if I want to rationalize the denominator, in this expression, so let's do 5 over 3 plus root 2. So remember yesterday we found something to multiply by that would make the denominator rational. So what do you guys think we should multiply by? So if I have 3 plus root 2 here, what should I multiply by in the denominator to get a rational number? Let's try it. So yesterday, this is kind of the approach we took. We just multiplied by the rational or the irrational factor. In this case, that would give me 5 times the square root of 2. And then in the denominator, that would give me 3 times the square root of 2 plus the square root of 2 squared. So I get 5 times the square root of 2 over 3 times the square root of 2 plus 2. Did I rationalize the denominator? I didn't, right? Because even though this term became rational, I had to distribute that square root of 2 to both terms, so the term that was already rational is now irrational. Any other ideas? Okay, let's try that. So 3 plus the square root of 2. So that would give me 15 plus 5 times the square root of 2 And then in the denominator, that's a horrible line. In the denominator, we would have 3 times 3, which is 9, plus 3 times the square root of 2, plus 3 times the square root of 2, plus the square root of 2 squared. So this one's okay, right? Because when I take the square root of it, I'm going to get 2. So that one's cool. We'll just make that a 2. But then these guys are a problem because that gives me 6 times the square root of 2. Right? What I want is for those two to cancel. So one of them would have to be negative. So what could I change up here to make one of these guys negative?
In front of the parentheses on.
Well, if you put a negative in, well, you'd have to do it to both.
Yeah.
Well, remember, we can make that right side, that factor, we can make it whatever we want. So we don't have to do anything. We can make it whatever we want it to be.
So it would just be 3 minus root 2.
Yeah, like if you look at the problem that we just did, the one before this, when we multiplied 3 plus the square root of 2 times 3 minus the square root of 2, we got a rational number, right? And that's our goal here. We get to pick whatever we want in that second fraction because we're making it equal to 1. It's the same on the top and the bottom, but we can make it whatever we want on the top and the bottom. So we're choosing something that is going to cause these two middle terms, which are the only two irrational terms that we get, to cancel off, which means one, we have to, that second term, we have to have one negative and one positive. And so that will give us 15 plus 5 root 2 over 7. So we are multiplying the numerator and denominator by the conjugate of the denominator.
So conjugate just like the opposite?
No, because the opposite of 3 plus root 2 is negative 3 minus root 2. Like the opposite changes both signs. The conjugate has the same two terms, but just the operation between them is different. So the opposite would be like if I multiplied it by negative 1. And so that would change both signs. The conjugate just changes one of those signs.
So, would you do this every time, or just?
Yes, so this is the process for rationalizing the denominator if we have two terms in the denominator. So if there's addition or subtraction in the denominator. Mm-hmm. So yesterday, just to remember, if I did 5 over 3 times the square root of 2, there's only one term in the denominator. And so that's where we just multiply by the irrational factor.
And you don't have to switch it to a negative or anything.
Right, because there's no addition or subtraction. So up here we have two terms. So there's addition and or subtraction and that's what we change, is the addition or, like either we do, if there's addition there, we do subtraction there. If there's subtraction there, we do addition there. Down here, there's no addition or subtraction, so we can't change it to the other one.
Okay.
So then it would be, if it was opposite, it'd be 11 then.
11?
Well, what if you have?
Which one?
Still, well, it would change that -2 to a +2, wouldn't it?
Which-
If the first term was a 3 negative, and then you did the 3 positive.
Right, you would end up with the same denominator.
Oh, it's still 7 either way.
Well, because 3 plus root 2 times 3 minus root 2 is the same as 3 minus root 2
Yeah.
times 3 plus root 2. Just switch the order of the factors. So this one would end up being 5 root 2 over 3 times root 2 squared. So that's 5 root 2 over 3 times 4. So the first thing you always have to ask yourself is, does the denominator have one term or does it have 2 terms? And that determines what you're going to multiply by to get a rational denominator.
And I suppose I'm sure it gets more complicated the more, like if you had more, what do you call them? So if I had the 5, the first thing we're multiplying times another different, like 3 over 4 plus the square root of 2. So then you have to add them all together, right?
If there's
Kind
two,
of just like we did with our,
if there's 2 terms in the denominator, you always use the conjugate of the denominator, regardless of what the numerator is.
right, so if the second set of in, I don't know how I'm trying to explain, like if you had 5 times 6 over the 3 plus square root of 2, and then, no, they're separate, is what I'm trying to say. So like 5 over 3 plus square root of 2.
Mm-hmm.
And then all times, say 3 over 4 plus the square root of 2.
Mm-hmm.
So then you would have to do the conjugate for each separate one and then combine them, right?
Well, I would probably multiply these first and then conjugate or then rationalize the denominator.
Oh, okay.
But like this one up here, like this isn't the problem.
Right.
Like we were just rationalizing that denominator. Okay, so let's do one more of these, and then we have a couple examples that are just kind of ones that look a little weird, so we should practice them. Let's rationalize the denominator let's do 1 plus the square root of 3 over 5 minus the square root of 3. So I'm starting with 1 plus the square root of 3 in parentheses on top, and then 5 minus the square root of 3 in parentheses on the bottom. So I put those parentheses there because there's addition or subtraction, just like we did with rational expressions. So what should I multiply by?
5 plus square root of 3.
Good. So 5 plus the square root of 3 over 5 plus the square root of 3. Because that's the conjugate of my denominator. So now we'll distribute. In the numerator, we have 1 times 5 plus 1 times the square root of 3 plus the square root of 3 times 5 plus the square root of 3 times the square root of 3. In the denominator, we have 5 times 5, which is 25, plus 5 times the square root of 3, minus the square root of 3 times 5, minus the square root of 3 times the square root of 3. Notice we're not canceling anything because there's terms, right? There's addition, subtraction. So now in the numerator, I have 1 plus 6 times the square root of 3 plus 3. Right? I combined like terms right here. What's wrong, Ben? It's okay?
Yes.
Oh, no.
Oh,
You
okay.
could see. You should speak up because this is a 5 right here.
Yeah.
Oops. Yeah, there's no one.
This is a 5.
Well,
Don't just take my word for it. Okay, then in the denominator we have 25. That one is for sure. And then combining like terms here, we get 0. Right? 5 root 3 minus 5 root 3 is 0. And then minus the square root of 3 squared, which is 3. So we're going to end up with 8 plus 6 times the square root of 3 over 22. But we're not quite done yet because it's a fraction, right? Do the two terms in the numerator of that fraction have any common factors? Two. So I'm going to factor out a 2. We get 2 times 4 plus 3 times the square root of 3. Remember that this 8 plus 6 root 3 behaves just like 8 plus 6x. So when I factor the GCF out of that numerator, it's just like factoring the GCF out here. Right? We're taking it out of our two coefficients, that 8 and 6. And then in the denominator, that is a monomial, so there's no addition or subtraction, so I can just do prime factorization. That's 2 times 11. And so we've got a common factor of 2 that'll cancel. Which gives us our final answer, which is 4 plus 3 root 3 over 11. Okay, we're going to do 2 more problems. We all good with this one?
Not yet.
Okay.
So when we get to the 8 plus 6,
Mm-hmm.
root 3 over 22,
Yep.
why are we going past that?
Because we want to simplify the fraction as much as we can.
Okay.
So just like last week when we were adding and subtracting rational expressions, after we simplified the numerator completely, we tried to factor it, right? To see if we could then cancel off any common factors. So same idea here. We did our multiplication, we simplified the numerator and denominator, and then since it's a fraction, we always factor the numerator and denominator to see if you can cancel any common factors. So that's true of any fraction you're working with, whether it has whole numbers in it or polynomials or rational expressions.
So with the 8 plus 6x equals 2,
Yep.
4 plus 3x, did you do that first or what's below it first?
Well, the only reason I wrote this is just to show you how I got this. Like that they're essentially the same. Like the factoring process is exactly the same.
Okay.
Like there's no x's in this problem, so this isn't actually like part of the problem. I just wanted you guys to see how.
We're still going to factor whole numbers whenever we see
Right.
them.
We're factoring the GCF out of the coefficient, regardless of if the other part of the terms is a variable or a radical or whatever it happens to be. We can always factor a common factor out of the coefficients. What's up?
On the last one,
Yes.
it was 15 plus 5 square root 2
Mhm.
over 7.
Yes.
Why wouldn't we factor that one?
So we could totally factor that as 3 plus, oh, I messed that up too. That should be a minus. Oh, I remember because we did it the other way first. We didn't change that piece of it, so that's a minus. 3 minus root 2 over 7. And the only reason I didn't do that is because I could kind of see that, like, I wasn't going to be able to cancel anything.
Okay.
So, like, when I look at that 15 minus 5 root 2, I kind of think to myself, well, the GCF is 5, and, like, 7 and 5 don't have any common factors. So if you can tell that there aren't going to be any common factors, it's fine to just leave it.
Okay.
Pretty much if the denominator can't be factored, you're done.
Unless, I mean, you want to be a little bit careful with that generalization, because if you had like 14 minus 7 root 2 over 7,
Well, because it's 7.
then you can factor,
7 out
right? So even though the denominator can't be factored, there's still a common factor there that can be canceled. So if you're unsure at all about if you're going to be able to cancel something, you should go ahead and take out any common factor that you can, just to see if anything cancels. But if you can tell by looking at it, like this one, we can kind of see that like 5 and 7 aren't going to have any common factors. And so that's the only reason I didn't pull anything out there. In fact, when I do these, like if the numerator has just one term, I usually leave it factored until I get to this last step, because then I don't have to factor it out again. Whereas like here I had 2 terms here, so I had to actually distribute and combine like terms to figure out if I was going to have a common factor or not. Any other questions on this one? Good questions.
It's just weird that the bottom answer, if you subtract 1 from 5, is 4 with the square root of 3. I mean, is that going to be, obviously it's not going to
feels weird to me because I don't feel like I can factor out a 2 from the root 3.
Right, that's why I was showing you like this.
Yeah.
Is like the root 3 is just this piece of it.
Gotcha.
And so what we're factoring our GCF out of is always just the coefficients. So I could put like, I could do like 8 plus 6 times like a flower or a banana. And it would factor the same way because all I'm factoring is the coefficients.
So you have 2 bananas.
Okay, we ready?
Yes.
Okay. So we're going to do a problem that's different, and then we're going to come back and do another one of these to see if we can remember 10 minutes later.
Good idea. Feel like this one's probably going to take us 15 minutes though.
No,
I feel you're right.
this one won't take 15 minutes at all. Okay, so we're going to do... I'm going to make sure I don't do the one that's on your homework. We're going to do 1/2 plus 1 over the square root of 2.
1/4.
So do I have common denominators?
No.
I do not have common denominators, right? Because 2 and the square root of 2 are not the same number, right? If you doubt me, just plug them both into your calculator. You don't get 2.
I trust you.
Well, I mean, if you square 2, you don't get 2, right?
Well, you can't split.
Yeah, you can. 2 times 2 is 4. So, what do I have to do to add 2 fractions? What do I need? I need common denominators. So in order to get common denominators, what I'm going to do is I'm going to rationalize this denominator first. So just in that term, I'm going to multiply by, well, let's see. So I have 1 over the square root of 2. Will it rationalize it to do 2 over 2?
No.
So what should I multiply by?
1.
Should it be root 2 over root 2?
Right, we want the irrational factor because there's only one term in the denominator, so we're just multiplying by whatever the radical is in our denominator. So we get 1 over 2 plus the square root of 2 over the square root of 2 squared, which is 1 over 2 plus the square root of 2 over 2. And now we have common denominators. So what's my numerator going to be?
1. Well, that's going to be 2 square, the square root thing, 2, whatever you want to call it.
What operation am I doing?
You're adding, but.
So what do you get when you add?
1 plus root 2.
1 plus the square root of 2.
Yeah.
Good. All over 2. We have to be careful to use the operations that are given and not just like change it to multiplication, right? Just because we have a 1 and a root 2 doesn't mean we have 1 times the square root of 2. So we just have to use what's there. And so I'm going to just go back and change this one to just to show you real quick. Another possibility is if this hadn't been a 2, if it had been, well, I'm sorry, does everybody have it written down?
Yes.
as is. Okay, so you don't have to change it on yours. You can write a new problem. But if this had been a 6 instead of a 2, the process would be identical up until this last step here. So if this was a 6, the first thing I would do is still rationalize that denominator. But then at this point, I don't have common denominators, right?
You have to go 3 over 3.
Yes, very good. So then I would do 1/6 plus the square root of 2 over 2 times 3 over 3. So we get 1 plus 3 root 2 all over 6. So the first thing we want to do is rationalize the denominators, or denominator, depending on how many are irrational. And then get common denominators. I guess that's just that one step where I did that. Then get common denominators. So this is a good example. Both of these are good examples to have in your notes, because these problems can look a little bit daunting, but notice that this is all stuff we've done before, like as far as like rationalizing the denominator, how to get common denominators, how to add fractions. So it just looks a little bit different. But again, as we've seen with a lot of other problems, if you kind of break it down into smaller pieces, we're doing one little problem when we rationalize the denominator. We're doing one little problem to get common denominators, and then we're just combining those.
So then if you had like the 1 over 6, if that was square root of 3, then you're just going back to the other process?
So if this is the square root of 3,
Yeah.
okay, so then we have two denominators that are irrational.
Right.
And so we would rationalize both of those separately. So that, again, that's two separate little problems. This is going to be 1 over the square root of 3 times the square root of 3 over the square root of 3 plus 1 over the square root of 2 times the square root of 2 over the square root of 2. So we would get the square root of 3 over the square root of 3 squared plus the square root of 2 over the square root of 2 squared. So we'd have the square root of 3 over 3 plus the square root of 2 over 2. And then what would we do?
Then you'd have to do
2 over 2.
2 over 2.
Yeah, then we'd have to get common denominators. So we do 2 over 2 and 3 over 3. So we get 2 times the square root of 3 plus 3 times the square root of 2 all over 6. So see how it's kind of, if you break it into smaller problems, like this one is just the same as the one we just did. You just happen to be doing this process twice and this process twice. So try to think of it in smaller pieces, and it's a little bit less overwhelming. Okay, last problem. I'll leave that one up there in case you still need it. We're going to rationalize the denominator. So let's do 3 over the square root of 6 plus the square root of 12. Go. You guys remember how to do it? Just about time to go, but I'm gonna show you the solution so you have it and you can make sure you're doing it right. So like in the numerator, notice that the square root of 12 can be simplified. So we would do 2 squared times 3 here. And then this is 6 minus 12. Right, and if you actually did the square root of 72 and the square root of 72, that's fine, but I knew these were going to end up being 0 anyway, so I just didn't trouble myself with figuring out what 6 times 12 was. And then we have 3 root 6 minus 3 times 2 root 3 over negative 6. Can I factor the numerator? What's my common factor? 3. So we have 3 times root 6 minus 2 root 3. And then in the denominator, I've got 3 times negative 2. So those 3's will cancel. And so you're going to end up with the square root of 6 minus the square root of 3 all over negative 2. Oh, I forgot a 2. I'm sorry. Oh. So root 6 minus 2 root 3 all over negative 2. Any questions?
So you can't cancel the 2 because it's with
Right, because we can't factor it out, right? We have to be able to take it out of the entire numerator in order to cancel it.
So if it was by itself, you could though, right? Or
Like, do you mean like if it was like this?
yeah.
No. Because it's being subtracted,
Oh,
right? So it's just like if you
Oh,
have
so it's
x minus 2 over negative 2,
yeah.
right? This is grouped. So it doesn't have a factor of negative 2
Oh,
because that minus 2, it's subtraction. And so same thing here, like this is a single factor.
okay.
So we have to be able to pull it out of the whole thing in order to cancel it.
Got it.
so it's up for
Any other questions? I'll leave that up if you're still writing. Make sure you turn in your homework from yesterday, and we will see you tomorrow. Have a great day.
Quiz
I'll be in
day
my
tomorrow.
office. Yep.